Okay, hello everyone. This is a video on Chapter 5 review questions from page 181 and 182. I'll just go through all the questions that I asked you to do. I'll start from 1, and there's a couple questions we'll skip, but mainly start from 1. I'll go to the end. Okay, so in question number 1, we have a girl puts a ball and it travels straight up into the air. Okay, it reaches its highest point after 1.5 seconds. So there's a couple things from that statement that we now know. Okay, and we also know that because it goes straight up into the air, then what happens is gravity will affect it, and gravity is caused by gravity. The acceleration due to that gravity is always 9.8 meters per second downwards. But according to the sentence, it initially goes upwards, it travels up into the air, and then it says highest point, so we know that it stops at that point. The highest point has zero velocity. Okay? All right, so first choice option we have is acceleration of the ball decreases as it travels upwards. That's not true. Acceleration is always the same, down 9.8 meters per second squared. Okay. The acceleration is constant as the ball travels upwards and then reverses direction. Ooh, reverses direction? That's not right, because not only is the number the same, but also the direction of the acceleration is always constant and the same too. So it's not B. The acceleration of the ball is greatest when the ball is at the highest point. Greatest means that means it must have less acceleration at some point during the time it travels up in the air. That's not true either. Okay, so D, because again, acceleration due to gravity means the acceleration is always the same. The acceleration of the ball is constant throughout the upwards and downwards motion. Yes, that is true. So D is number 1. Okay, number 2 is asking us, what is the initial velocity of the ball as it is launched into the air? So into the air, what velocity did it start at? Well, we know it's upwards, so we have this. We want to find what that is. We do know A, acceleration, because the initial velocity is upwards and acceleration due to gravity is down. That means we have to make that value negative now. Okay? And then we also know that what was the initial as it launched into the air? Well, we also know that eventually it will stop at its highest point. Okay? So that will be V, and we know how long it takes to get to that highest point. According to the first part, it says it took 1.5 seconds to do that. Okay, so now that we have 3 variables we know and one that we want to find, we can choose the equation that best fits. And if you look at your formula data sheet, you'll find that this formula is the one that matches all those variables. Okay, so we'll rearrange this so that we solve for u. Well, if you move u to this side, you can move this over first, I guess, and then that way, if you did that though, it'd be v minus at like this. Okay, and then, but we usually like u on this side, so I'm just going to make everything move over to the other side. Just reverse it so that it's easier to read. Okay, now we're going to substitute our value, 0 minus, and then this is still going to be negative 9.8, and it's going to multiply the time, 1.5, and you'll find that these two multiply to become a negative, and then the negative makes them all positive. And so that means this number will be about 14 exactly, I think. I don't know if it's exactly 14. Let me just check my calculator. 9.8 times 1.5 is 14.7. Okay, so there's our initial, and there is the unit for velocity, and if we really want to be good, we write the direction and it's up. Okay, so there's number 2 done. You can pause that to go back and look at the numbers. 3, calculate the maximum height reached by the ball. Okay, so the maximum height reached by the ball means at the highest point, right? Highest point. Okay, so then that means it's a displacement. We want to know that. So what things do we know? Well, we just finished finding the initial velocity, so maybe we can still use that. But we knew at the highest point it's 0, and we know that because this is up, acceleration due to gravity is down and is negative. And so now we can use these variables if you wish. There's more than one way to do this, depending on if you use time rather than final velocity. Then that would be a different equation. But based on what we have here, we would use this equation because it has all these variables. Okay. So we want to solve for this. Maybe best to rearrange everything. You can see these two add, so when we move this over, it's going to minus this one, and then it'll, because this is with s and they're multiplying s, we'll divide everything by this. Okay, so this moves over, v minus u, and I'm just going to arrange to make sure s is over here, so v minus u squared, and then everything divided by this to get rid of it and move it over. Okay, and once we do that, we get a 0 minus, and then the initial velocity squared, divided by 2 times acceleration. We said it's negative because we understood it's the opposite direction of the initial velocity. Okay, and then from that answer, just use your calculator. You know, I'm going to square this. We get some number, and then we're going to divide it by all this, divided by, just put a bracket here so I can, I'll just start over, and just so it's fresh for you, we'll use this one, okay? So we got negative 14.7. I think I'm going to have to put the brackets around it just so I don't multiply the negative when I do the squaring, and then this will be 2 times negative 9.8. Okay, and it should come to a positive answer. Good, because negative divided by negative, and we get 11.0. Okay, so the way you round that is 1, 2, 3, and then there's a 2 there, so that's 0 meters. Okay, so there's number 3. We're not going to do number 4, we said. I'm going to skip that one. But we are going to do the next few. So number 5 means we got to read this graph. I'll just zoom in a little bit. There we go. Okay. So, according to this graph, we have a position time graph or a displacement time graph. As you know, displacement is s, and there's meters. Okay, so it starts time 0. It's starting at 200 meters. The graph shows the position of a motorbike along a straight stretch of road as a function of time. The motorcyclist starts 200 meters north of an intersection. Okay, so it's already 200 meters north. During what time interval is this motorcycle traveling in a northerly direction? So here from 0 to 10, you can see it's not changing, so it's not traveling in that direction. So it actually, here we can see that it increases the displacement in the north direction. All this is north, and all of this negative is south direction. Okay, so he's heading towards the north because his north is getting greater, his north value. All right, so for us, it's between 10 to here, which is 25 seconds, is in the middle of 20 and 30. Okay, so there it is. Traveling in a southerly direction, part B. Well, we said that southerly means the opposite. We're going to lose displacement, so it's going down this way. And we can see it starts going down this way here, starting from 30 seconds and stopping here at 45 seconds. So from 30 seconds to 45 seconds, it's going south because we're losing displacement. And then stationary, well, there's two parts. We know in a a displacement time graph, or VT graph, any horizontal line means constant whatever. In this case, displacement is constant, so he's not changing his displacement, meaning he's not moving. So we got 0 to 10 seconds, and we have 45 to 60 seconds. Okay? Okay, let's go. When does the motorcycle pass back through the intersection? Okay? Well, it said in our description at the beginning that the motor starts 200 meters north of the intersection. So north, that means the intersection must be 0. When does he go from where he started all the way to back to 0? Right here. And I think it's between 40 and 45. So for us, at 42.5 seconds. Okay, and it's the difference between 40 and 45 seconds. Calculate the number 7. Calculate the instantaneous velocity of the motorcyclist at each of the following times. So 15 seconds. A is at 15 seconds. Okay. 15 seconds is, we go to the time axis, we see 15 seconds here, and so that's that point here. It is not this. This is only displacement. We know that velocity, or instantaneous velocity, is the velocity at exactly 15 seconds. And we know for a displacement, or a VT graph, the slope of the line gives us our velocity. Okay, so in this situation, we just find the slope. And this point of 15 seconds is along the same line throughout the time between 10 and 25 seconds. So the instantaneous velocity is the slope along that line. So we can use this line to find the slope that this point is part of. Okay, so I'm going to use the whole line because that's easiest. And the whole line gives us nice numbers. So we just draw a little right-hand triangle. You can see it starts at 200, going all the way up to 500. So 200 to 500 means it added 300 meters in a time of 10 seconds to 25 seconds, or 10 seconds plus 15 seconds is 25. So that would give us instantaneous displacement of, instantaneous velocity of displacement, which is 300, divided by time, which was 15 seconds. So we can see that he moved at 20 meters per second. Okay. Showing that time. Okay. Let's see what's happening here. Part B is very similar. It's at 35 seconds, but 35 seconds. Oops. Let me just erase this part. 35 seconds means is right here, and you can see that it's part of this slope. So the instantaneous velocity is that slope as well. But this time the slope goes down. So what's going to happen is we're going to get negative values, a negative velocity, because it's heading in the negative direction. Okay? Downwards is negative velocity. So slope is velocity, and the direction the slope goes tells you if it's positive, like this one, or negative. Okay, so we'll just choose 2 points along this whole slope. I'm going to choose here. No, that one's not great. So I'm going to choose a great number. That one's not great because it's at 42.5, which is kind of an awkward number. But we'll choose this intersection because it's exactly on 40 and 100. And then I can choose another one. If I just want to use this one, it's fine. I can use anything along this slope. So I'm just going to make my right angle triangle from there. And so that first one was from 300 and going downwards vertically, it's to 100. So that's a loss of minus 200 meters. And it took how many seconds to do that? Well, this first one starts at 35 seconds and the second one starts at 40 seconds. Okay? So that means it's 5 seconds. So we have the displacement change in 5 seconds. That means our velocity is going to be negative 200 divided by 5 seconds, and we get 40, or I should say negative 40 meters per second. I'll just write this a little more clear. Negative 40 meters per second at 35 seconds. So whether it's at 35 seconds or 40 seconds or 30 seconds or 32 seconds or whatever, as long as it's part of the slope at any moment in time, then it's going to have the same velocity. All right. Now it says for the 60-second motion, calculate the average velocity of the motorist. Well, average velocity, if you read your notes, means the total distance, or displacement, I should say, because we're talking about velocity, divided by the total time it took to do that. Okay? And the total time, they say right here in the question, I'll just write total as well. For us, how do we get total displacement? Well, we go back to the chart. We look at where we started, and at 0 time is where we started, so we were already at 200 meters. And then 60 seconds means here. Now we look at that difference. Well, it went from 200, and here it's minus 100, so it's just a matter of that. We went down 1 to 300 meters. Okay, it's negative. It's negative because, well, we went down. We went from 200 to 100, negative 100. And that took 60 seconds. So our average velocity was negative 5 meters per second. Okay? Or you can write it that as 5 meters per second south. Okay? Because there is a direction in the question. It says north, blah, blah, blah. Same thing up here. These ones, if we wanted to write the direction, very easiest for it to do that. You can write like that, and because it's the positive value, but if it's the negative value, you write the positive value, and then you write the direction, which is opposite that positive direction, north. Okay? Okay, so we're done all the way there. We're going to go up to number 9 and 10, and the rest. Okay? Let me just clear some of this. A skier is traveling along a horizontal run at a constant, it looks like constant, 10 meters per second. After falling over, the skier takes 10 meters to come to a rest. Okay, that's a lot of information. I'm going to write it down right away. So I know U is 10 meters per second. I know the distance he took to stop was 10 meters. And we know that he stopped because it says he came to a rest. So this is 0. Okay, so that's the information we know so far. Which of the following best describes the average acceleration of the skier? Well, if we really wanted to find that average acceleration, so we want to know acceleration, and knowing these variables, then we would have to use this equation to find out. Because it has those variables, and that's how we can solve. Okay, again, we got to isolate for A here, so we're going to move this over and divide those two by 2 and S. So it would look like this. A would be by itself. This moves over, and it's going to be V minus U squared. and then divided by these two that multiply a. Okay? And so, again, it's negative, whatever this number is, 10 squared, because v is 0, so 0 minus is going to be a negative value, and then 2 times 10. And we can see that this will be 100 negative divided by 20, so we get negative 5 meters per second squared. Okay? Which is right. It's causing the skier to stop, so that should be a negative number. We don't know the direction of the skier, so that's okay. It says number 10 now. Calculate the time that the skier takes to come to a stop. Okay, so we have acceleration, we have u, we have v, so why don't we use the simplest equation. So v equals u plus a times t. Again, this is from your formula sheet. Choose the correct formula that you need. V is 0. I'm sorry, I should rearrange my formula first because it's easier that way. I want to solve for t, so there's v and u. Okay, so I want to solve for t. What's going to happen is this is adding these two, so we do that one first. V minus u, and then a is multiplying t, so we're going to divide it by a. So negative 10, because it's 0 minus 10, divided by a, which is going to be negative 5. And then you can see negative 10 divided by negative gives us a positive 2 seconds. Okay, so there's 10. Okay, let's see, number 11 and 12. Number 11 is we gotta follow this information. So an athlete in a training for a marathon runs 15 kilometers north along a straight road before realizing she has dropped her drink bottle. She turns around and runs back 5 kilometers to find her bottle. Then resumes running in the original direction. After 2 hours of running, the athlete reaches 20 kilometers from her starting position and stops. It says, let's take a look at the question. We underline that because sometimes we don't know what information we need right away. Okay? But something like this, where it's multiple direction changes, you may want to draw a diagram. So why don't we do that first? 15 kilometers north. Okay? I'll just label that 15 km. And then she turns around and runs back 5 kilometers. Okay. It doesn't matter that I don't have this exactly over top. It's just to show me what direction and the lengths that she went. 5 km. And then she, after running for 2 hours, she reaches 20 kilometers from her starting position. So she actually started here. So that means she ran back this way until she reached a total of 20 kilometers away from where she started, okay? If you look at this though, she ran 15 kilometers, then 10 back, and then another distance that way, so that her total away from her starting position is 20. So if you do some easy math, it's 15 minus 5 is 10, and then another 10 to add up to a total of 20 kilometers. So this must be 10. This may be useful for us. It says calculate the average speed. Okay, first of all, speed can't matter about displacement. Speed is about total distance. So we have a total distance of 5 kilometers, plus she ran another 5, plus she ran another 10. Okay, so by drawing this diagram, it helped me clarify all the total distances she ran and her displacement. So this is displacement because that's what the last sentence said. And then the total of all that is the distance. So let's find that out. So her average speed, this is speed though, So I'll just write that down. Total distance divided by total time. So total distance is 15 kilometers she ran north first, plus the 5 that she ran going back south, and then another 10, so that her total distance from where she started was 20. And it says she ran that in 2 hours. We have our distance in kilometers. We have our time in hours, so we're just going to write that like that. So it's 30 divided by 2 is 15 kilometers per hour. Okay, that's A, 12A. Now, B says, what's her average velocity? Well, for velocity, we know she started here. She started down here, and then she ran north a total of 20 kilometers. Doesn't matter that she ran back 5 and then she ran another 10 to go north. The athlete reaches 20 kilometers from her starting position and stops. So that is displacement. And for average velocity, I put this arrow to distinguish it from the speed. It's just the displacement, which is 20 divided by the total time, which is still 2 hours. And then we can see that she ran an average of 10 kilometers per hour. Okay? Now, to change that in part B to meters per second, this is 12, right? Yeah. To meters per second, then what happens is, that was 11. That was 11, and this is A, 12A, and then B would be, take this, divided by 3.6, and then we would get that in meters per second. See how it was like 2 in the hat? That means 2.7777. So 7, and then we're going to round this 7 to 8. And the direction, if the question says direction 2, then we know we're going north, because that's where she ended up here. She finished north over her position. Okay, let's continue on. Okay, so of course you can pause this video anytime you like. I'm just going to start with 13 here, and then finish the rest, hopefully. Okay, 13. There's a few questions here for it on both pages, I believe. Yeah, there's a few questions down there. Okay, so a skier starts from rest. Okay, good. That means we can write that right away. It's very easy. And accelerates uniformly. If it travels 2 meters, so that's S for us, in its first second of motion, so that means t equals 1 second, calculate its acceleration. All right, easy, right? So we want to find A. So from this, S, U, T, and A, well, we would choose this equation here. Okay, so because it starts from rest, this makes this part very easy. It's 0. We know the displacement's 2. Why is that important? Because now we can rearrange this more easily, Okay, so we want to isolate for A. Let's just write this out first so that it's a little easier. Sometimes it doesn't help to rearrange stuff like this one until we can get rid of one of the t's. Okay, so that's going to be 1 times half is half, right? So we'd have half times A equals 2. And so we arrange, so that means A is multiplying this, so we'll divide that side. 2 divided by half equals 4. So 4 meters per second squared. Okay, forward, yep. So we got that part. B, its speed at the end of the first second. Okay, well, we know the acceleration, we know U, we want to find this one, and we know the time. is equal 1. Okay, so very easy for us to choose this equation. And so it's 0 plus 4 times 1. So its velocity will be 4 meters per second in the first second. Yeah? That's the speed. The distance that the ski jet travels in its second second of motion. All right, so we know that A is still going to be 4. The time is going to be 1 more second, right? The second of seconds. And we know that after the first second, see, from previous part B, at the end of the first second, we know that he was traveling at 4 meters per second. So that will be our new initial velocity. And we want to find the distance it travels during that second. Okay? Well, we know it started at 4. We know it traveled for the next 1 to the second. And so we use this equation again. But this time, you can see that u is 4 times 1 plus half of the acceleration, which is half of 2, so 4, I mean. And the next second is only 1 second squared, 2. Okay, and then for us, that means S equals 4 plus 2. 2 times 1 is 2. Okay, so in the second, it travels 6 meters. Okay, so that means from time 1 to time 2 seconds, it traveled 6 meters. Okay, 14 and 15 we were not going to do, so we're going to skip to question 16. The following information relates to question 16, okay, and 17. 2 physicists, physics students conduct the following experiment from a very high bridge. Tao, it's Vietnamese, she is, I'm assuming, drops 1.5 kilogram shot put from a vertical height of 60 meters, while exactly at the same time Benjamin throws a 100 gram mass with an initial downwards velocity. And for Tao, it says drops, so that's very important information as well, from a point 10 meters above Tao. Okay. Let's see what question we're going to calculate the time that the shot put takes to reach the ground. Okay, so we'll go back here. For Tao, she drops it, so U equals 0. We don't really care about the mass. Remember, the mass doesn't matter in our calculations. None of the formulas and equations have mass in it, so that's not relevant for us. But the distance she travels is 60. That's relevant. And because she drops it, A is a positive value, 9.8 meters per second squared down. Okay. Takes the time it takes, so we want to find T. Okay. So I'm just going to move over here. T, we know A, we know U, we know S. Okay, so from that, again, we can use or choose this equation and input the data that we have. So displacement is going to be 60. All of it's downward. She's dropped, so everything's downward, everything's positive. It's good for us. So it was 60 meters downwards. Initial velocity is 0, so that makes this part easy. Half of acceleration is 9.8, so that's 4.9, and it's multiplying t squared, which we need to find. So there it is. If we isolate for t, it's t squared equals 60 divided by 49, 4.9. And then to find t, well, we just take the square root of this, and so we don't need that there anymore. Okay? Okay, so the square root of 60 divided by half of the acceleration. All right, so we push s to d to make it a decimal, so 4.499. That 9 makes this 10, that 10 makes this 5. So t equals 3.50 seconds. Okay. That's that. B, the 10, how long does it take for the 10 gram mass to reach the ground? Okay, so for us, for that one, it did have initial velocity. That was Benjamin throws it initial downwards velocity, so that's 10 meters per second from a point 10 meters above tau. Okay, so for tau, she went 60 meters. Benjamin's even higher than that by 10 meters, so his is going to add that too. A is still the same acceleration. We still want to find time. Some things I don't write. I mean, you guys should know what acceleration is now. So B, again, S U T plus half a t squared. Okay, so this one's going to be a little different because now we have this too. So we have 7t for displacement. We have 10 times t is the same for both of those, plus half of a, which is 4.9, because that's half of 9.8. And then t squared. Okay, so now we have three numbers, and to solve for this, we need to make everything to one side and make it equal to 0. Okay, so it's easiest when this is positive, so we'll keep all this on that side. This is 0, we got to bring this over, move this to the front, so 4.9 t squared, and then this one next is positive, and when you move this over, it'll be minus 70 instead of positive. Okay, and now we're going to use our calculator to help us do this. Now, because this is t and t, that's the same variable, and it's a quadratic because it's squared, we got to change our calculator. So we do that by going to mode, this button. We want to change it to equation 5, and we want it to be exactly like this, something squared, then the same something, and then nothing there. So that's number 3 here, as you can see. Okay, number 3. And then for these, you just write the number in front, the numbers, just the numbers. So 4.9, enter to make that there. That one's 10. Now this one's minus 70, so this will be negative 70. Gotta make sure that's negative 70. Enter. It's negative 70. Enter one more time. Gives us the first value of t. Just to double check, you'll probably get the second value that's negative. Yep, and we don't want the negative because time can't be negative. So I'll just get back to there. You can just keep pressing enter to get that, and then t will equal 2.89. That's a 4, so that stays 9. Okay, so it takes a little less time because it started at a faster velocity. Okay, moving on to 17. At what time does the 100 gram mass overtake the shot put? Ooh, okay, so they throw this exactly at the same time. Let's see. Okay, so what information do we know about that? Well, let me move over more. There we go. Okay, so when do they meet, or when does the shot put pass the weight? Well, remember, this one's going down and the shot put is going to go down. And when they pass, they're going to be at the same displacement from where they started, yes? Okay. So if we consider the displacement for tau as the change in displacement where they meet is s, Well, this one would be S plus that 10 meters that Benjamin started at before. So this would be S plus 10, okay? Their displacement is the same, S and S plus 10 more. The question asks us, what time? So T is the factor that we don't know, okay? Yep. So again, for this one, we know that this equation is for that, because we know the initial velocity, acceleration, whatnot. And then same with this one. They have exactly the same equation, okay? So for tau, she's gonna be this one, okay? Tau is gonna be u times t plus 1/2 a t squared. And Benjamin's gonna be the same, but remember his s has plus 10, so he's gonna have plus 10 over here, which means minus 10 over here, okay? So that means for him, he's gonna have all the same thing for himself, Benjamin, tau. They have exactly the same acceleration, and their time will be the same too. Okay, but for him, he has that 10 extra meters that he has to go. So, okay, let's see what happens now. Why did I put the negative over here? Because remember that displacement is the same as hers, but plus 10. Okay, so it looks a little complicated at first, but once we walk through it, you'll see it's okay. So again, we want to find out what time it takes them to be at the same displacement after they're dropped. So that's why we're equating these two together. But Benjamin, his was S plus 10, so we move the 10 over, and so on this side, with the rest of the variables, it's minus 10, okay? All right, let's start with tau. She started at 0 meters per second, so that's 0 for her. And then we'll just simplify everything else. Plus half of the acceleration, it's downwards, so it's 4.9. Half of 9.8 is 4.9 times t squared, and it'll equal this side. And we know that for Benjamin, his initial velocity was down to 10 meters per second, and so that's times the time. And same here, half of 9.8 is 4.9, so plus that, because they're all in the same direction, t squared, and you'll see that this is the same as that, minus 10. Now, you see that they're both 4.9 t squared and on opposite sides, so they actually cancel out. Like if I brought that over, it would just subtract that. So what I end up with is 10t minus 10 equals 0. Well, if I move this over, it would be that, and we can see this t equals 10 minus 10 equals 1 second, okay? So at 1 second, they will have fallen the same distance, not the same distance, but they would have fallen, and Benjamin's weight will be the same distance or past tau's as it goes down past her, okay? Okay, so we'll move on to the next question. I think it's 14. You can always go back. No, I'm sorry, question 18, 19, and 20. And I think it relates to the graph here. So this is a VT graph for Olympic cyclist as he travels north along a straight track. So it's important to read this because sometimes they give you the direction. And so the positive direction is north, okay? Okay, so this is all, you can see all this is above the zero axis or the horizontal axis, so it's all positive direction that he would travel, or displacement anyways, but not necessarily positive you know, I don't want to ruin it, but you'll see what I mean. What is the average velocity of the cyclist during the 11-second interval? Average velocity, whoops. Well, average velocity means we have to know the total displacement. Yeah. V average means displacement divided by the total time. Okay, so how do we find displacement? Again, for a VT graph, displacement is under the shape of the graph line. Okay, so this one you can kind of estimate. You can see that this shape here, and if we stop here, because I want to use this triangle because it's a nice triangle here, okay? And then you can see that's just the rest of this shape here. And then we'll just use this because that's a nice shape too. And it's pretty much the same. So this is the trapezium, rectangle, and triangle. All right, so why don't we do that? You could do, what was this? Another trapezium here. You put a line here, and it'd be it's rectangle, trapezium. But I think this is maybe probably the easiest one. There's so many ways to break up into the different shapes, okay? So just make it easiest for yourself. So we have trapezium, rectangle, and triangle. Okay, so first one for the total displacement would be rectangle, which is going to be a height of 8 or a velocity of 8 and a time of 9 seconds. So that's easy. 8 times 9. Okay, there's our first displacement plus sorry, that should have been 2, but this second one is this is going to be 1, 2, 3 seconds, and then this parallel side is 1, 2, 3, 4, 5, 6, 6.5, so 6.5, and the distance between them is from 8 to 14, so that's 6. Okay, so we're going to have 3 plus 6.5 divided by 2 times the distance between those two sides is 6. So there's our second one. It's easiest just to do it all in one calculation, guys, because you don't want to, mess up somewhere. And then you can check to make sure that each part is correct. And then this one is a right angle triangle. Very easy for us. The height is from 14 down to 0, so 14. And then the base is 2 seconds, so 2, and that's 14. We want half of that. So 2 times 14 divided by half, or divided by 2 is half of that. So we add it all together. Let's put it in my calculator. Make sure that it all looks the same. We got to change this back from the previous one, so just go to mode and then 1 for computation. Okay, first one is, why don't I just do it all? The total time is only 11 seconds, right? 11 during the 11 seconds interval. So this is 11. So why don't we do it like that? Let me just get this one. First one is 8 times 9. Close, plus, and then we want all this is a big bracket, and then also this 3 plus 6.5 divided by 2, move it over, multiply 6. So the nice thing about these calculators, it shows exactly like how you read it, plus this 2, so that's another fraction button. I don't think we have to put the brackets on this one because it's just like that, 2. Okay, and then I'll go down, divided by 11, make sure all of that's the same. Press enter, there's our answer. It's 10.40909, so that's going to be 1. So that's going to be 4. Okay, 10.4 meters per second north, because it is all positive and it's north. Okay, he was traveling north. Yep. Okay, so that's the average velocity. Which one or more of the following statements correctly describes the motion of the cyclist? He's always traveling north. Yes. When we're looking at a VT graph, anytime you're above the zero or the horizontal line, it's all positive direction. Doesn't matter if you're going faster or slower or slowing down, okay? So that's true. He travels south during the final 2 seconds. This is the 9 and 11. His velocity is not traveling south. His velocity is reducing, yes, but that means his acceleration is negative, not his velocity, okay? Negative velocity means he would be down here somewhere under the zero line. That's not true. He's stationary after 8 seconds. Well, the 8 seconds here, that's not, remember, horizontal line for VT graph means that velocity, remember this is velocity, is constant. He's not changing his velocity, so that's not true. He returns to the starting point after 11 seconds. That is also not true. This point here is just saying that he stopped. That's all. Okay, he was going north the whole time, going at constant speed, going faster, going a constant speed that's higher now, and then finally slowing down really quickly, and then stopping. But not at any time did he turn around. Okay, last part of the question, 20 for the graph. Calculate the acceleration of the cycle at each of the following times. All right. Acceleration for a VT graph is slope. So 1 second, it's part of a horizontal, A equals 0. There is no acceleration. That's a horizontal line. At 5 seconds, well, we just draw a line through there, okay? That best matches that point through here. Okay, so it's a nice point. It was a straight line. You can see there's a nice point here and a nice point there. So we'll just stop there, find the change in velocity and find the time it took. So we went from 10 to 14, that's 4. And we went from 4 to 6 seconds, that's 2 seconds. So A equals 4, change in velocity divided by time, 2 meters per second squared. Okay, north. If you really want to make it, you can say north. And then 10 seconds is exactly here, and you can see it's part of that whole line. Remember, if a point is part of a whole slope, then they have the same slope. So the acceleration is part of the slope. The whole slope, which is calculated, it's easiest to go from there to there. So we can see that that's negative 14. Started from 14 meters per second down to 0, so it's negative 14. And it took 2 seconds to do that. A equals negative 14 divided by 2 equals negative 7. Or we say 7 meters per second south. Okay, because that's the opposite direction. That is negative. Negative of north is south. Okay, guys, good luck. Hopefully this helped you out. Again, at any point in the video, you can just pause it, go back and review what I said and how the question was done. Okay, good luck on your test. See you in class. Bye.